Welcome to the final lecture in this installment on analog to digital conversion. This lesson focuses on metrics and errors associated with analog to digital conversion. ADCs have various metrics by which you can choose the correct analog to digital converter for your application. The most prominent of these metrics is the resolution of the analog to digital converter. And the ADC resolution defines the possible number of output codes of that particular ADC, which is described by the number of bits. For example, a 2-bit ADC will have 2 to the 2 or 4 possible output codes, and a 12-bit ADC will have 2 to the 12 or 4096 possible output codes. So the resolution of these two different ADCs would be 2-bit and 12-bit respectively. Ultimately, the resolution of the ADC is going to be dependent on the type and construction of the ADC, but typically 8 to 24-bit ADCs are commercially available. Another common metric for analog to digital converters is the least significant bit of a particular ADC. And bit is sort of an odd term to use here because for an ADC, the least significant bit is actually the voltage, which is required to change the output code by 1 bit. So for example, that might mean that I have a voltage at my input that changes my output code for a 2-bit ADC from 01 up to 10. Or if I had a 4-bit ADC, it would change the output code from 1011 up to 1100. In either case, I've increased the voltage just enough to increase my output code by 1 bit. So that voltage, that least significant bit voltage, which we're calling a voltage even though it has to do with bits, is defined as the full scale range voltage divided by 2 to the m bits, where m is the number of bits at my ADC. So for example, if I have, say, a 4-volt full scale range and I have a 2-bit ADC, my least significant bit voltage is going to be 4 divided by 2 squared. 4 divided by 4 is 1. So there's a 1-volt least significant bit for this example. If I had a more capable ADC, say a 12-bit analog to digital converter, for the same full-scale range input of 4 volts, I'm looking at a least significant bit voltage of about 1 millivolt. So for this 12-bit ADC, if I increase the voltage at the input to my converter by about 1 millivolt, my output code will go up by 1 bit. Certainly there are a host of other metrics to consider when performing a trade study on which analog to digital converter you should choose based on your application. And to evaluate those metrics, you want to dive into the data sheets for the particular ADCs that you're considering. In this example, we have an ADS-1250. This is a Texas Instruments ADC. And we see from the data sheet, it's a 20-bit ADC, and it's a Delta Sigma ADC in terms of its construction. It's interesting, though, to dive into the details. If you look at, say, the second bullet here, the datasheet is telling us that even though it's a 20-bit ADC, it's really only effective resolution of 18 bits up to a certain operational data rate. So for data rates up to 25 kilohertz, I'm getting 18 bits of resolution. Therefore, this notion of data rates and sampling rates is another important metric to consider when selecting an ADC. So you want to pay attention to the sampling frequency with which you'll be using your analog to digital converter. We also need to consider the quantization error imparted by the use of the analog to digital converter. And this arises from the fact that we're dividing these outputs into discrete levels or quanta. And a way of thinking about this quantization error then is the approximate input voltage that I'm recovering from these codes, which is defined here as the code divided by 2 to the m, where m is the number of bits. Multiply that by the full scale range of my ADC. That approximate input voltage that I'm recovering would be equal to the true input voltage Vin. That would be the ideal scenario. However, in reality, that's certainly not the case. A simple example here is to go back to that 2-bit analog to digital converter that we've been discussing. If I had an input voltage Vin of 1.1 volts, my output code would be 01. And if I had an input voltage Vin of 1.2 volts, my output code would still be 01. Both of these codes, however, result in an approximated input voltage of 1 volt, and 1 volt is certainly different from 1.1 volts and 1.2 volts. So this quantization error is going to be a direct result from the fact that we are grouping these input voltages and assigning them to discrete output codes. And there are a number of consequences then for the metrics that we've just discussed relative to the performance of these ADCs. First, this error is going to be dependent on resolution. So as my number of bits increases, my quantization error will decrease. I'll have a better approximation of that input voltage. Additionally, this error is going to span one LSB, one least significant bit. So what we find is that this quantization error is bounded by plus or minus 1/2 of an LSB. And finally, there are a range of other errors that can creep up and affect the performance of the ADC, and often they can be more impactful than the quantization error. I can have offset errors, I can have gain errors, linearity errors. And as you see in this example datasheet, these can add up to a significant amount of LSB. In this case, we have an ADC from a Texas Instruments ADC. This is an MSP 430 series. And I can see here that if I look at the total unadjusted error, my typical total error is going to be on the order of plus or minus 2 LSB. But in some cases, it can be a maximum of plus or minus 5 LSB, which can be quite significant depending on how you're using the ADC for your particular application. So if I look at the full-scale range voltage of this ADC, it looks about 3 volts here. That means the least significant bit voltage will be 3 volts divided by 2 to the 10, or approximately 3 millivolts. So if I have plus or minus 5 LSB, I'm actually looking at plus or minus 15 millivolts, which again can be significant depending on how you're using the ADC and what you're trying to sense. So it is fantastically important when you're choosing an ADC for your application. Evaluate the number of bits, evaluate the sampling frequency, make sure it's going to meet the requirements for your application, but then dive into the datasheet and take a look at the errors associated with the ADC under the particular operating conditions, and make sure you have a comprehensive understanding of how this ADC operates and make sure it's going to meet the requirements for your particular application.